Right. Hello, everyone. We are going to commence this month webinar conducted by Institute of Physics Sri Lanka. I'm Shayamila Gamage, President of Institute of Physics Sri Lanka. First of all, I would like to warmly welcome all the participants of this webinar. Thank you for being here today also. We have been organizing this webinar to promote physics and its application. Also, we are the public on what key topics related to physics. Before introducing our resource person today, I have one announcement. So please mute your microphone and we'll give you time at the end of the session to ask questions. And also during the session, you can type your questions on the chat box so that I can ask your questions from the resource person. So today's webinar, we have invited Dr. Shayamila Gamage from University of Toronto, Canada, to give a presentation on atmospheric physics related to topic. Let me welcome Dr. Shayamila Gamage on behalf of IPSL. Thank you, Shayamila, for accepting our invitation. Before formally begin the presentation, let me call upon Dr. Chathuru Nupiarachi, co-editor of IPSL and convener of the Committee of Popularizing of Physics, to introduce today's resource person. Thank you very much. Over to Dr. Chathuru.
Thank you so much, sir. I warmly welcome our resource person, first of all, Dr. Shayamila Gamage. She is a postdoctoral fellow at the University of Toronto, Department of Civil and Mineral Engineering. Currently, she is working on a project to estimate the impacts of greenhouse gases, reduction on the effect of air pollutants on population health issues in Quebec, Canada. And she has obtained her undergraduate degree in physics from the University of Sri Jayawardenepura. And she already completed her PhD and master's in physics at the University of Western Ontario, Canada. She is interested in research related to impacts of climate change. And she has gained experience in the fields of lidar theory, inverse modeling, homogenization of climatic data, source apportionment, and atmospheric physics. So without wasting much time, I would like to hand over the digital platform to Dr. Sham. Over to you.
Sorry, thank you so much for I'm just having a little bit of technical difficulties. Can you all see my screen first of all?
Yeah, we can see it.
Perfect. Okay, thank you so much, Professor Shayamila Gamage, and for inviting me, and Chathuru for organizing this. So I'll be presenting a little bit of my work from my previous postdoc at University of Montreal in Canada. So this work is related to understanding the air quality. So the topic I'll be discussing today is identifying the sources of local and long-range transported particulate matter, which is PM 2.5. That is going to be our main focus. So a little bit like what I'm going to be talking, what is particulate matter, what kind of emission sources, and why we are interested looking into this, and the methodology. And I'll be taking in one example site, and then I'll be going into details of that. And if we still have a little bit of time, I would like to present some of my work related to Sri Lankan air quality as well. So to begin with, what is particulate matter? So it is very tiny particles considered to compared to an human air. It's still really small, you can see in the picture. So it contains of microscopic solids or liquid droplets, and these are too small, so it can be inhaled. So typically we can find PM in dust, smoke, soot, and several, there could be many emission sources. So I'll be using this word a lot in this presentation, that is EPA. So EPA stands for Environmental Protection Agency in the United States. So they do a lot of work related to atmospheric physics, like literally for air quality and many climate change related topics. So EPA has defined 6 common air pollutants, or also known as criteria pollutants. So PM, particulate matter, is one of them. So the rest of the pollutants are carbon monoxide, lead, ground level ozone, nitrogen dioxide, and sulfur dioxide. And EPA also defined, introduced 2 categories when it comes to particle pollution. One is the inhalable coarse particles. These are literally the road dust and dust from industries, and the particle size is between 2.5 micrometers to 10 micrometer in diameter. But today our concern, we'll be talking about fine particles that usually found in smoke and haze. So they are in particle size that's about 2.5 diameter. So the origin of PM, the sources can directly emit PM to the environment, or it can be created by different chemical processes that's happening in the atmosphere. So there are several. We can define few of the major types of sources. One is the mobile sources like vehicles, and stationary sources such as power plants and several industries. And we have natural sources, forest fires and volcanic eruptions. All these things can directly emit, or also the emissions will be processed to become PM 2.5 or particulate matter in the atmosphere. So why we're studying this? There are several climate impacts associated with particulate matter pollution, or in general air pollution. So poor air quality is always linked with climate change. But the thing with the particulate matter, it is not a single type of chemical or species. It's a combination. It's the combination of different chemical particles like species. Therefore, it has various different physical properties and chemical properties. Therefore, it's hard to isolate the impacts of particulate pollution in the as in climate change or health impacts. So for an example, if you reduce the amount of black carbon in the atmosphere, that could lead for global warming. But if you reduce the atmospheric sulfate content, that could increase the global cooling. So this is a little bit complicated. However, overall, the air pollution can lead in rising temperatures and longer allergy seasons that we see in especially Europe and North American region. And it could also affect the changes in weather. But these things you always know, people talk about air pollution and climate change. But what I would like to highlight today is the health impacts of PM 2.5 and particulate matter in general. So when it comes to health problems, the size of the particle is directly linked with the potential of causing health problems. So the particles that are less than 10 micrometer diameter, they pose greatest threat to human health. So it can, because they're too small, they can be inhaled and they can get deep into our lungs. And sometimes it may get into our bloodstream, causing blood clotting and even having heart attacks. So this looks something, okay, now I'm going to show you a little bit more detail. How does PM cause health effects? So it can cause not just the lung related issues, but it can also create premature death and less life expectancy, the number of years that we are living can be reduced. Heart attacks, preterm birth, low birth rates, all these things. So here in this map, the graph, I'm showing, okay, let me get my laser pointer. So you can see the number of deaths by risk factor. These are the numbers that we get from 2017 world data. So the total annual number of deaths because of air pollution is around 4.9 million. So every year, around 4.9 million people die because of bad air pollution, like bad air quality. So this is a serious concern. It is called as a silent killer, and there are lots of studies and research that's happening in the area of understanding the impacts of air pollution on human health. So in 2019, there was a report by State of Global Air. So they named countries in Asia and Africa to have the highest risk of exposing themselves to harmful soot or particulate matter, especially for PM 2.5, because we rely a lot on coal-powered energy power plants, and we use a lot of charcoal, biomass burning kind of for cooking and agricultural purposes. So about 25% of the deaths that are registered in India itself, it's happening due to air pollution. And overall, 65% of the deaths in Asia have the same cause. So if you think this is a concern only for the adults, which is not, as you can see, we have premature death, preterm birth, low birth rate. So according to the same report in 2019, they say children born today will be exposed to so much toxic air pollution over their lifetime that can reduce, like they can dramatically reduce their life expectancy. So in average, we could lose about 20 months of our lifetimes. In some areas of the world, it could be 30 months. So this is a serious concern. So this is why we are trying to understand what's happening and how we can stop this effects. So the first steps towards reducing PM emissions or improving air quality or regulating emissions would be to identify the sources of emissions. So this needs to be done locally, regionally, and globally. So this is why, like, once you identify the sources of emissions, then you can come up with, like, you can establish goals, you can create regulations, and then you can implement new policies. So controlling these emissions. So today I'll be focusing on understanding the local sources and a little bit into the emission that's been transported over to the regions. So that's why it's highlighted. So now let's get into the methodology section. So today I'll be presenting the method called source apportionment. Source apportionment is the identification of the air pollution sources and quantifying them, their contribution to the total pollution levels. So this can be done based on, there are several approaches of understanding the types of emission sources. So if a country has emission inventories, for an example, like in Canada, we have an emission inventory introduced by Environment Canada. They pretty much record everything. So for an example, we have an industry that emits SO2, they emit NOx, they emit PM. So they know exact amounts of emissions. Once you have that, you can do research related, you can use a source identification method that uses emission inventories. But today, I'm going to talk about something called a receptor model. So the concept of the receptor model is literally the mass conservation. So for an example, the idea is we measure PM 2.5 at a certain location. We call it a receptor site. So at the receptor site, we measured 10 grams of PM 2.5. So if the mass is conserved, the total amount of PM 2.5 that are emitted by different sources, so it could be like traffic emissions, industrial emissions, the summation of all the PM 2.5 emitted by all these factors will be equal to what we measured. This is the idea of the receptor model. So there are several receptor models that are available, but today I'm going to present the method that I was using. This is called positive matrix factorization. So the PMF, it's one of the very common factor analysis technique in our field. So this was developed like pretty recently, I would say, compared to some of the scientific equations and formulas that we're using. So this was developed in 1994. So this it very simply. So if you look at the equation here, it looks like a linear regression. So the X are the concentration of species. This could be particulate matter. You can enter elements, you can give metals, you can get ions. So any kind of concentration of species is going to be X, and we will have multiple samples of these species. So the idea is the same thing as I explained before. It's the mass conservation. So we record a certain concentration of a species, and that is emitted by F is the factors. We could have different factors such as vehicular emissions, industrial emissions, secondary pollutants. So these are the factors, and G is the contribution, relative contribution, or what's the percentage of contribution, like pretty much the weighting of the factor. So the summation of this relative contribution times the factor profile gives us the summation of the concentration that we measured at the receptor site, plus or minus we have a residual. There's a difference between the two equations. Just to balance it out, we have residuals. So this is pretty much it. You can have multiple species. So like I mentioned before, EPA, Environmental Protection Agency, they have introduced a software that we can easily use to do PMF. So EPA PMF you can enter a bunch of measurements, PM 2.5, like I haven't listed, but you can, like I mentioned, you can do elements, ions, and all sorts of measurements that goes into the model. So how the PMF, EPA PMF works is like you have this equation, but just to make sure that we are reaching an optimal solution, we run this model iteratively until we get a minimum cost or a loss function. In this case, our loss function is the Q ratio. So Q is the ratio between the residuals that we saw here and the uncertainty of the species. Usually when we do a measurement, it comes with the uncertainty. So we have X and the uncertainty corresponding uncertainty U. So Q, the idea of EPA PMF is to minimize the Q ratio. So at the end, PMF gives us two main outputs. One is the total, the factor contribution to the total PM 2.5. For an example, in this case, PMF have sold 6 factors. So summation of all PM 2.5 emissions from all these 6 factors should be equal to 100%. So this is what it's showing. The second thing they're giving us is like they take each species and they give us the relative contribution of each species to the factor sample. So these are the two main outputs. So PMF, they're getting the result section, like getting the optimal solution, is pretty simpler than most of the mathematics that we are doing. But the challenging part is to understand the factors and labeling them. So we'll get into that section in a bit. So today I'll be using an example of one of the source apportionments that I've done for Quebec City. So Quebec City is the second largest metropolitan area in Quebec, which is Canada's largest province. So the city, it is also the 7th largest metropolitan area in Canada. So you can imagine how big it is. One interesting fact about Quebec City is that there's a Quebec port. This is one of the Canada's busiest ports, and it also connects it has the seaway between the Europe and the Great Lakes. So there's a lot of shipping related activities happening in the area, and it's very industrial and urban. So we are trying to look into, we are trying to understand what kind of emission sources are in the city, and if there's any pollutants that's coming from neighboring cities or countries, kind of. So where do we get our measurements? So the measurements I'm going to present today, we're getting it from the National Air Pollution Surveillance Program, which we call NAPS. NAPS was founded in 1969. It's been running for 40 years. They have over 200 air quality monitoring sites located all over Canada. So the idea of NAPS program is to collect the air quality pollutants and get the measurements, and then provide accurate and long-term air quality data for the people. So in Quebec itself, we have about 6 to 10 NAPS stations. And in Quebec City, the town, the metropolitan area that we are interested, we have one NAP station that is shown in the map in red. This is Quebec Aviu Limoilou station. So this is located about 1 kilometer to the west of the Quebec port, like a very urban area. And you can see in the map here how populated it is. It is highly populated, so it's known as a general population exposure site, and there's a lot of residential emissions, and it's a large population site. That's how the NAPS identify this location. And so once I use the data from this NAPS station, I'll give you an idea what kind of measurements that I give to the model. So the measuring period, the study period that I'm looking into is from 2012 January to 2014 December. So the PM measurements are made once in 6 days. So in the figure, you can see the red line is the Quebec monthly mean PM 2.5 concentration. And the other 2 sites are located in Montreal, which is the largest metropolitan area in Quebec. It is, compared to Quebec City, it's even urban and industrial. So, however, we don't see any contrasting or significant difference between the 3 sites. So the Quebec City lays pretty much in the same range as the other 2 sites. So for the NAPS measurements for the site, we get elements, we get metals, and we also have ions. One interesting fact about these measurements, so when we are doing source apportionments, there are a few traces that we would love to have that makes our job easier. So one would be biomass burning traces and carbon, organic carbon, elementary carbon emissions. Unfortunately, we didn't have those traces for this site, but still we were able to get really good results. And some of the industrial traces, such as selenium, antimony, selenium, tin, antimony, lead, the signal to noise ratio is a little bit lower side. Therefore, we weren't really able to isolate some of the important emission factors, but I'll show that in a bit. Another thing I want to mention here, in Canada, we do have Canadian air quality standards. So nationally, we are supposed to keep certain amount of emissions. So for a 24-hour average, 24-hour day, calendar day, the average amount of PM 2.5 that we can have in the air is 28 micrograms per cubic meter. This limit was set in 2015. But because there were certain policies that's been applied, there's regulations for emissions that was happening. So by 2020, their target was to bring it down to 27 micrograms per cubic meter. So the annual, the standards were like 10 micrograms per cubic meter for 2015, and 2020 was 8.8. So these are some of the other sites. These are sites located closer to the Greater Montreal area. And this is our site, which is located in Quebec City. All these sites are well below. The study periods are a little bit different, but still, all these measurements, all these results, what it says is like we are well below the Canadian air quality standards. So overall, the air quality in the cities are pretty decent. And also, one thing you can see here, I didn't want to add a trend line, but if you can see, there's a decreasing trend of PM 2.5 over the years. This is due to some of the industries were closed and they have regulations for industrial emissions. Especially in Quebec, we have an issue that's related to winter wood burning. A lot of people use residential wood burning during the winter times. So now they have made new regulations from 2014, actually 2016 on. They have asked people to upgrade their furnace. They cannot use the old ones. So that way they're cutting down a lot of wood emissions, wood burning emissions that's entering the atmosphere. So now let's go to the PMF results. So like I said before, the results that we are getting is pretty, getting the results is easier, but understanding them and labeling them is difficult. So imagine what I'm getting from, like, imagine I don't have these labels. I don't know what it is. From PMF, what I'm getting is these bar charts. So how do we identify what factor is this? So for that, you have to look into the chemicals or the species that are highest contributing for each factor. Let's take a couple. So let's look at the first one. We have over 30% contribution of PM2.5. And then we have highest contribution, that's over 70% coming from ammonium. And then we had the second highest from sulfate. So anyone in our field, by looking at ammonium sulfate, this is labeled as secondary sulfate, the sulfate that is created during the chemical processes that's happening in the atmosphere. So it's easy to identify. You can have several metals in it. However, the most highest contributing factors and species are ammonium and sulfate. There we go, it's secondary sulfate. Now, if I talk about this factor over here, so this factor, we see about 15% more, a little bit over 15% of PM2.5 contribution, aluminum, silicon, calcium, titanium, and we do have manganese and iron, and a little bit more from other ions as well. So calcium, aluminum, titanium, these are traces of soil dust. So, or we call mineral dust. However, in this case, we have vanadium and manganese. Vanadium and manganese are traces of vehicular emissions. So it's related to tire. When the tires and like the brake wear, it emits these particles. So in this case, this is a mixture of mineral dust, road dust, and vehicular dust. Therefore, I'm just going to generally label it as dust. So if we had, let me take one more example here. So let's take this example down here. We have high contributions from potassium and zinc. Potassium is a great tracer when it comes to biomass burning. However, like I mentioned before, we don't have organic traces or the wood burning traces like levoglucosan tells us about wood burning. So if we had those traces, we would have had a separate factor. PMF would have solved a separate factor for wood burning or biomass burning. But in this case, we didn't have those. So the optimum solution kind of merged several factors into one. So that's why like here we have biomass, a wood burning tracer, potassium, and we have zinc. Zinc can be emitted from several sources. It could be industrial, it could be from vehicles, it could be even from waste burning. So for now, we'll forget about this title. So it could be biomass burning and something else. So once you have, once you kind of have an idea what kind of sources you have, then you go do further analysis, try to identify and relate it to the emission sources that are in the area or the region that we are looking into. So before going into that, I would like to show some other stuff. So I said, other than the bar charts, we also get the total PM2.5 contribution as well. So here we're seeing secondary sulfate factor contributes most to the total PM2.5 mass, that is about 34%. And the second highest contribution is from secondary aerosol. And dust contributes about 14%. We have salt, don't worry about aged salt yet. It's salt, so 16% of PM PM 2.5 is from salt factor. So, and then we have biomass and waste incineration, 8%, and crude oil about 5%. And now, how does it changes with the seasonality? What's the seasonality? When you look at the seasonality, I would like to point two important things here. So let's first look at the salt factor, which is the brown one. You can see the salt factor peaks in winter. This makes a lot of sense for countries that actually have a winter, because like during winter time, we use salt in the roads for de-icing purposes. So there's a lot of resuspension of road salt that's in the air. So that's why we are seeing a lot of peaks in aged salt during winter time. And the second factor that we are seeing is secondary aerosol, which is in orange color here. So you see secondary aerosol peaks in summer. So what is secondary aerosol? So secondary organic aerosol. It is a little bit more complex. These secondary aerosols generate due to the oxidization process in the atmosphere. So it could be like combination of carbonic compounds and volatile organic compounds and get together, and it creates this secondary aerosol product. So what happens in summer is, because of the enhanced photochemistry, we will have more secondary aerosols compared to the other sources out there. So this is what's happening in summer. So the remaining of the factors, they change a little bit. That could have a little bit of seasonality in it, but it's not very evident compared to the other ones. So that's what our major concerns. So those two are there. Now let's go try to understand what are the sources and how to differentiate the local sources and long-range emissions. So there are two techniques, because I'm running out of time and I'm going to go into a lot of details. So the local emission sources are identified using the conditional probability function. This is literally a probability of an air parcel arriving at a certain receptor site from a specific wind direction, and that wind should carry the highest concentration of the pollutants. So in this calculation, we require local wind data, which is wind speed and wind direction. When you want to study the long-range transport, the air parcel should be arriving further away. So in this case, we need enhanced atmospheric models, meteorological data, and it's a must that we calculate the back trajectory. That means we have to locate a certain air parcel and look at where it came from. You go backwards and try to figure out the origin of that air parcels. For this, we had to use the model called hybrid single particle Lagrangian integrated trajectory. It's available online. You can use it. It's called high split. It requires meteorological data. For this, you can use any data assimilation method. So in my case, I used the GDAS1 with 1 degree resolution. And there are several softwares out there that allows you to calculate the CPF and PSEF once you have that basic information. The calculation process is not difficult. You can use the OpenAir, which is an R package. Anyone can use it for CPF calculation, or there are several other MATLAB related and Igor-based softwares for the potential source contribution function. If anyone's interested, I can talk about it later. So once we have these two calculations done, we can identify the local emissions and long-range emissions. So I'm going to take a couple of examples here. So one of the interesting outcome from my is factor that we had high concentrations of potassium and zinc. So like I said, potassium is a biomass burning tracer and zinc is the problem. Where is zinc coming from? So for this, so now we have to look into our CPF. So the CPF is calculated. We take the highest 10% of the pollution of this factor, and then we sort it out with the wind direction, where there's this highest 10% of pollution coming from. So when you look at it, so the blue, there's a probability of you getting it from several directions, but the highest, we see a peak, high probability of having a potential source of zinc and potassium emission that's happening between north and northeast direction. So this is our site, and this Thiru waste incineration. This is very interesting because Thiru, Canada, this is the largest waste incinerator, or the place that we burn waste, residential waste, industrial waste, all sorts of waste is burning at this location, and it is well known in apparently in this part of the city. They know this place as high levels of carbon monoxide and furnace emissions. So when we see that in our CPF, we could easily recognize, okay, so this has to be something related to waste incinerator. So that's one way of identifying local sources. So this is where we have our site, and it's a little bit towards the north, and we have a lot more things happening around this area. So however, the main emission source that could possibly emit zinc is the waste incinerator. So we relabel this factor to be waste incineration and biomass burning. By any chance, if we had like carbon emissions or wood burning emissions, we would have seen something like this. This is from a different site. You will see this seasonality. So if you see winter peaks, that's happening in the biomass burning tracer, that is related to wood burning, because people use residential wood burning during winter time. But sadly, we didn't have it. But just based on the CPF and the sources of zinc, we can identify this factor. The second factor is pretty straightforward. So it is age salt. So like I said, salt is easy to identify: sodium chloride, magnesium, if we have those species in a factor that is salt. But why it is age salt? So not just CPF and just normal statistical analysis, we can also look into the ratios of each and every species that is inside these factors. So when you calculate the chlorine to sodium, magnesium to sodium, these ratios, and you compared it to the ratios that are in the fresh seawater, so what we found is the ratios that is inside this factor is not equal to, they're not even close like to the factors in fresh seawater, to the ratios. Therefore, this is not this factor that we are seeing in the PMF. It's not fresh sea salt. It has to be age salt if you look into the literature, if you have nitrate in it. So there's some chemical processes happening, so it can be easily identified as age salt. So based on our location, what are the possible, and then also you can look into the seasonality or how it changes over time. We see the winter peaks. So we don't have to think too much. We can literally say, okay, this is related to one of the possible source of the age salt factor is the sea salt because of the seasonal variation. And then the second possible factor here, we are really like, the site is by a lake, like a river. And there's a lot of port related activity. So marine aerosol is one of the other possible factors. So we have to validate our results. So we're gonna look into the CPF now. So based on the CPF, we are getting the highest 10% is coming from several directions. However, we see higher amount of possible, the highest possibility is in the direction of southwest and south. That's where we have the St. Charles River, most of the port, this is the seaway. So a lot of marine related activities happening here. So that's, again, reconfirms our assumption. And then also this area over here is highly residential compared, and it's like so dense and compact. It has several major highways running near this area. So that alone points out to the road salt. There's residential areas, highways, a lot of road salts that'll be added. So that the CPF confirms our assumption of having two possible sources in the age salt factor. Now, how do we do the long range transport? So based on our back trajectory calculations, it is one thing that's very important when you're doing long range transport. We have to always think about how long a certain pollutant can stay in the atmosphere, what's their lifetime. So secondary sulfate, secondary aerosol, these are known to have longer lifetime. So when you look at it, so the secondary sulfate, this is where we have our site, and we see like probability of having like emissions coming from southwest of United States, like including states like Ohio, Michigan, Pennsylvania, and like even Indiana. So this region, and we see a little bit coming from Ontario, and like there's a power plant in Quebec. So this is towards the edge of the Quebec. So secondary sulfate, it's ammonium sulfate, if you remember. So where does it coming from? So in literature, people have done a lot of studies. In US, there are lots of coal power fired electric facilities. So these power plants emit sulfur dioxide, selenium, and all these things contribute to creating secondary sulfate. And it's being pushed towards Quebec or Canada. So that is where we get most of our secondary sulfate coming from. And then if you look at the secondary aerosols, like I mentioned before, it's a combination of different chemicals. So mostly the secondary aerosols are emitted by traffic and industries. So industrial emissions and traffic emissions get together, make secondary aerosols. And once again, we see it's in the between like the New York and this west of US provinces, like states, and also from the Ontario. And we see near our dot, which we have our site, there's a little bit going around. That is the pollution that's coming from Montreal. Montreal has about 6 or 7 metal smelters, all refineries. They all emit SO2. They all create secondary aerosols. So everything is being pushed towards Quebec City. And then the next factor, this is one of the very interesting results we got, that is crude oil combustion. So the crude oil factor is the factor that we have highest highest contribution from vanadium and nickel. So in anyone in our field, if it's like vanadium and nickel, that's related to the ship emissions. So, but when we looked at the potential source distribution function, we are seeing high, like having a potential source near the offshores, like they're not even in the land itself. We see some points in the shores, like in actually the sea. So what's happening here? So we looked into the Canadian oil gas industry, and because crude oil is vanadium and nickel, like I said, when you combust this crude oil, it emits that. So the ones that you're seeing here, these are from Newfoundland and Nova Scotia area. We have in Canada, they have 2 large offshore projects. One is the Sable offshore, that's for oil and gas mining. So whatever happening here, it's being transported to Quebec. And then we see a lot of potential sources along the Great Lakes. So remember, I mentioned Quebec City is the seaway to the Great Lakes. So lots of shipping activities that's happening. And along this area, along this route, there are a lot of like smelters, oil refineries, coal-related activities, a lot of industries happening along this path. So all these emissions that's been transported, the emissions from crude oil combustion is transported to Quebec City. And surprisingly, we see some hotspot, like the potential sources that are in northern Ontario and northern Quebec. So what's happening there? In the northern part of the country, what happens is in Canada, they do not have like electric generation from hydro. So what they use is like crude oil. They use crude oil to generate energy, electric energy. So that's why we see all these potential sources in these areas. So that explains the crude oil combustion factor that we are seeing in Quebec City is being transported from several parts of the country and also from United States. So, and then if you think, okay, so is it that's it? Like you just literally label local and long range transport? No, some of the factors could have both of them. Like for example, let's take the crude oil. So it could relate to the offshores. There are potential sources being transported. Also, there are some emission factor sources that is in the city. So there are local factors. To verify there are local factors, we looked at the CPF. So of course, you can see it's well spread it out. We get the highest 10% from pretty much every direction, and we see a little bit compared to the other direction. There's a little bit towards north and northeast direction. That's where we have this terminal. This is the Wopak terminal of Canada. This has very large tank storage facility for all these things. So this is a potential source, potential local source. And then that's what this map, the CPF, is pointing towards. And then we also looked into the ratios of vanadium to nickel. So in literature, if the vanadium to nickel ratio is really high, if it falls between 2.5, like 3.54 kind of range, high range, that is from the shipping emissions. Sorry, can you guys hear me? Okay, so I'm gonna quickly go to the end. So there's Sri Lankan air quality. I didn't have time to go over it, but you can always look into the United States EPA Colombo Embassy. They do have air quality monitoring site. I downloaded their data and I looked into how the air quality in Sri Lanka works. So in average, we are in moderate. It's not the best case. And you can easily relate that to the different monsoons that we experience. And good news for Sri Lanka is there's a declining trend and negative trend in PM 2.5. And you can also do the PMF analysis, PSCF analysis to figure out where the PM is coming from. So we see emissions coming from West Bengal reaching Sri Lanka. So West Bengal is one of the highest polluted provinces, states in India, but I've only done 3-day back trajectories, but if you do more, you will see more pollutions coming from different regions to Sri Lanka. So you can, once again, relate all this to the Sri Lankan monsoon. So if anyone's interested in doing research related to this, I'm happy to talk about it. So summary, PMF is a great tool for source apportionment, and you can use PCF and CPF and PSCF for long-range emission figuring out. And several important factors we found in our research. One is the waste incineration and biomass burning factor that is from Quebec City incinerator. And we found potential long-range transport from Canadian offshore oil and gas mining and shipping emissions along the St. Lawrence Seabay. Take-home message would be PM, especially the fine particle, has various health impacts on public. It is a silent killer, so we have to take actions to control emissions. So air pollution can decrease person's life expectancy by a year or two, and 25% of the deaths is in India is due to air pollution. So that is related to us as well. So we don't have to wait until the government make regulation. We can do our own thing. Try to reduce using your car or your vehicle multiple times. Try to make all your trips in one go. If that's possible, take public transport. Waste management and invest in renewable energies. All these things you have heard, but it is important not just for ourselves but for the future generation as well. So finally, I would like to thank my previous supervisor, Dr. Patrick Hayes, and the group at University of Montreal, especially Michael from the Climate and Atmospheric Research Center in Cyprus, and finally for funding this project to Ministry of Environment in Quebec. Thank you. So sorry for taking a little bit more time.
Thank you very much, Shamda. That's an impressive work. And if anyone would like to ask a question, please feel to ask. Okay.
So yeah, Dr. Shayamila, so it's, can you hear me?
Yes,
Yeah.
please go ahead.
Yeah, it's a very interesting one. So, how about model applied to the Sri Lankan one? So, are there any challenges to implement your model to the Sri Lankan data and kind of thing?
So the issue with the Sri Lankan data, it's just like, it's not a proper air quality monitoring station. So it's just the US embassies having their own thing. They provide air quality index, just, just to inform people if it's a good air quality day or a bad air quality day. And they also have PM 2.5. Other than that, they don't have anything else. So this is why we cannot use the same method that I've used for the other cities to identify the local sources. That's why I more looked into the long range transport. So if there's a chance that I could get my hands on to an emission inventory, or like, a little bit more details about the local emissions, what industries we have, then we can approach it in a different way. Rather than going to a source apportionment, we can use some chemical transport model and stuff to identify these factors. Yeah.
Yeah, thank you.
Any other questions? So I have a question about your model minimizing the Q ratio.
Yeah.
So I couldn't understand what is the
so this is literally the
uncertainty.
sorry.
What do you mean by uncertainty of UIJ? How do you
Right. So
measure, or is that measurable or no?
yes. So like I said, the measurements comes along with their uncertainty. So U is the uncertainty that measured uncertainty. So it's literally the method detection limit from the instrument. So certain measurement along with their uncertainty, which is U, and the E is literally the residual. We're trying to minimize, like, the gap difference between the actual species and the summation of all these factors together. So that's pretty much it. It's a little bit different. It's not regulated than a normal cost function, I would say. It's just this ratio. That's what they're doing.
Right.
Yeah.
Thanks.
I mean, all these things, if anyone's interested, most of these sources are available online. So EPA, Environmental Protection Agency, if you look into that, they do have a lot of tools out there for students to use. And you can try, I mean, this data for Colombo, I just downloaded it by myself. So you can do the same thing. If anyone's interested doing any project, just download it from the sites and then try to use the softwares and tools available in EPA.
And also I noticed that monthly mean PM considered in high in 2012 in one of the graph. What would be the reason?
So there are several things that was happening during this period, 2012, pre-2012. One is they had several smelters and oil refineries. Like in Canada, there are about 9, and I think 6 of them are located in Quebec. So one of them actually, they closed it during that time. So the emissions went down drastically. But sadly, I didn't include the measurements before that. If we had it, you would have seen that drop. So we were interested in the 12 and 16 period. That's where they implemented the wood burning regulations as well. So they they came up with the idea in 2012 and then they started implementing it. People started using new furnace and stuff. So that way, a lot of the emissions being regulated. So start to seeing the decline in PM emissions.
How about recent values? I mean, after the this pandemic situation.
So there have been research happening right now. I haven't, there's another person who's working on that. We see less values, but interestingly, I saw that in Sri Lankan work that I was doing. If you see the average air quality index here, so 2020 is the black line. So after March of 2020, so the value starts to go a little below the 2019 value. So this could be an implication. This could be due to the less vehicles entering Colombo during the COVID time. So we do see it in Canada as well. So I personally haven't gotten myself into that part, but definitely we do see a lot of improvement in air quality.
So, but in addition to Embassy of USA, about the Environmental Authority?
I personally don't know. I was interested in looking into this because of the same reason, like what's happening to air quality pre-pandemic and post-pandemic kind of. So the only data set I could get hold of was this EPA, like the US Embassy data set. But if there is any, I know I personally did my internship at Central Environment Authority. I know they do a little bit of air quality monitoring, but if they have these measurements, then yeah, we can do a lot of things with that. I looked into literature. I couldn't really find any study from Sri Lanka related to air quality, but there's lots in India. So that is again related to Sri Lanka as well by looking at the trends and patterns. So whatever that's happening in India matters to us. So yeah, so I think, yeah, if we can get hold of that data, if the Central Environmental Authority has something, yeah, then I'm more than happy to look into that.
Thank you. Any other questions? There's one question in chat box actually. Used to control the emission by identifying source and regulate them. Is there any other approach to remove PM 2.5 like chemical or other way? I cannot understand anyway. So can you understand this?
Yeah, I think I get. So other than regulating, so this is something, like I said, it's a little bit complicated. You cannot just isolate one PM 2.5 source and then go from there, right? It's just a matter of which one we are going to remove. It's you can't really filter it out. You can't use chemical processes just to filter it out. So the best way is to get into a balance. So one of the main pollutants, air pollutants, is traffic emissions. So what you could do is what's easy is to regulate the type of fuel that we are using for the vehicles. That way we will release less pollutants to the environment. Like the combustion will be more, if you repair, like, clean your exhaust in your vehicle, that will help as well. So things like that, it's more convenient. I would say it's the most easiest approach, I would say, rather than like chemically removing. I don't think that's it could be one thing. And then again, these are complex compounds, chemicals, all getting together and making this, like, volatile carbons and making secondary aerosols, all these things. It's really hard to isolate. So I would say it's not something that we can do. Yeah, I would rather go for the policies and regulations and try to minimize the effects.
Any more questions? There are no more questions. I would like to thank Dr. Shayamila Gamage for his interesting presentation. And I would like to invite our Joint Secretary of IPSL, Dr. Vasanthi De Silva, for word of thanks. Over to Dr. Vasanthi.
Yeah, thank you, sir. So very good morning to Dr. Shayamila. So I think it's morning time for you. Yeah, so good afternoon for others participant from Sri Lanka. So I would like to thank our guest speaker, Dr. Shayamila Gamage, accepting our invitation to share your research experience with us. I believe this is another new field and wonderful branch of physics. So we are not getting touch very much of these type of research field. So your talk on identifying sources of local and long-range transported fine particulate matter was contained a lot of very interesting facts. I believe participants received good flavor of how research going on related to the atmospheric physics. So really appreciate your comprehensive and nice explanation on this topic. So this is the time to acknowledge our president, Professor Shayamila Gamage, and IPSL committee members who are organizing this webinar series. So thank you very much for your continuous effort to success this webinar series. Also, thank you all participants present here for paying your attention and learning today. So I'm looking forward to seeing you at the next webinar. That means it's our August webinar. So have a nice day to all.
Once again, thank you very much, everyone. Thank you, Professor Shanta and Dr. Chaturi and Dr. Vasanti for organizing this. And thank you for inviting me. And thank you very much, everyone, for joining us today.
Thank you very much.